Okay, so our problem today is if we have data pairs like height to width or number of household televisions to life expectancy, how do you interpret the values that you get for the linear equation when you regress the data down to a straight line? There's one question, is how do you interpret the two values, the y-intercept and the slope, when you regress the data down to a straight line? And then how do you use that linear model to, and here's two new words, interpolate and extrapolate. Okay, so let's get started. So what I'd like to do, let's get my ugly face out of here. What I'd like to do is start with some new data. So I'm going to go to some data I scraped from the World Health Organization. And here it is. So in mainland China, they reported lots of different cases. How many total recorded cases, number of people who have recovered, and number of people who have died. Each day, starting with, my data started with January 22nd, which I call day 0. That's called normalizing the data. That's one of many ways of normalizing the data. So I start off with day 0 of having 502 cases. Actually, they started a little bit ahead of that, but I thought 500 cases is when you actually have enough cases where standard models start kicking in. Okay, so they started with 500 cases, and I go all the way up to yesterday. Well, I mean, that doesn't mean anything to you. 3/19/2020. So that was day 57 for them, where they had, and here I'm actually using the number of active cases. So not total number of cases, but the number of active cases. So right now, as of 3/19, they had officially, mainland China had officially a little over 7,000 active cases. I've also, starting at a date which I think was in 3/08, was when the U.S. first had recorded over 500 active cases, to kind of line it up with the Chinese data, the mainland China data, and calling that day 0. These are the number of active cases we've had up to 3/19, where we had 13,000 active cases of coronavirus reported in the U.S. and its territory. So what do we want to do? We want to look at the first 11 days. Why 11 days? Because that's how much data we have for the U.S. We're going to look at the first 11 days for mainland China and their number of active cases during that time. We're going to copy it, Control C, and I am going to go to StatCrunch and paste it. And I'm going to put in days as our first variable and active China as our second variable. Now, here's what I want to do. We can do a scatter plot of this, but I want to go ahead and do a scatter plot and put a linear regression in. So we go to Stats, Regression, Simple Linear. And our first variable is going to, our explanatory variable will be days, and our response variable, our y variable, will be active China. And we compute. Now the first screen we get, let's bring this over here. The first screen we get is got all the nuts and bolts of what just got computed, and things that we will never talk about in this class. But the one that really matters to us is that we've got active China, this linear model here, that the active China, the number of active cases we have in China, predicted by the number of days, is given by almost 13,000 times days minus 18,000 active cases. So our slope is 13,000, about 13,000, and our y-intercept is minus 18,000. We'll talk about how to predict that, but let's just see a picture of this. Oh, before we go on, let's look at r squared. R squared right here. Whoops. is almost exactly 0.9. So let's make sure we interpret that. So coming over here, there's our picture. The line that we see there is the line given by the linear equation, the linear regression line, the least squares fit line. It's the line that has it minimizes the sum of the squares of the vertical distance of each of those points to a line. So there's lots of lines you might want to draw there, but this one minimizes the sum of the squares of the vertical distance. And the r squared, in that case, the r squared of 0.9 can be interpreted as saying is that yes, as I look left or right across the days, those points change. They don't stay the same value. We don't have the same number of active cases all the way across. We have some days less active cases and some days more active cases. But as a 0.9, that means that 90% of the change that we see going across can be totally given to us, interpreted as, or explained by, or modeled by. I kind of like that better. Can modeled by this linear equation as a linear change, as just a simple slope of the values of the active cases going up as the days increase. Okay? And now remember that when we talk about these models, we're not talking about causation. We don't mean that the days, which day it is, causes these active cases. We're saying that of all the variables that are involved, that the variable of which day it is, and the variable as a explanatory variable, and the variable of active cases as a response variable, that relationship, 90% of that relationship can be explained by a basic, simple regression linear model. Okay? All right. Let's go back and interpret the equation for that line. So get a good look at that line, the red line into the 11 dots, and let's go back and interpret that equation. So let's go back. I'm just going to hit this back button, and I have it highlighted. No, I don't. That's the r squared. Liar. Okay, there it is highlighted. The active cases is modeled by negative over 1,800 active cases plus almost exactly 13,000 cases times what day it is. So that means on day 0, this model predicts a negative 1,800 cases. Well, that's ridiculous. How do you have negative 1,800 cases? Well, remember, when you push a model to the endpoints, or if you push a model past its endpoints, and anytime you ask a model to tell you something past the range of the data, that's called extrapolation. Extrapolation. And when you ask a model to predict values within the data range, that's called interpolation. Interpolation. So predicting things outside the range of the data, extrapolation. Predicting things inside of the data range, interpolation. Now, interpolation close to the endpoints is a dangerous game. Even close to the endpoints is a dangerous game. The more you get towards the middle realm, the better it is. Because remember, every linear regression model goes through the mean. The mean of x, the mean of y. X bar, y bar. That's a pretty good estimate of the x's and the y's. But when you get towards the endpoint, like here, when we're at 0, we know that our value, the number of active cases when we had on day 0, because we defined it that way, in mainland China was around 500. And yet the linear equation predicts minus 1,800, which is a ridiculous interpretation. Trying to put in days before that, we would just get more negative, which makes no sense. And what's going on here is that that's the y-intercept. And the y-intercept is always interpreted as, what does the model say when the response data is 0? So when the response data is 0, what does the model say? Okay? It may make sense, it may not make sense. Okay? The slope, however, is something you can use. Here, almost 1300 is interpreted as a rate, as a ratio of the y over the x. And you've done rise over run since day one of algebra. And that is something that everything is aimed at. That's what Calculus 1 is about, is the study of rates and density, because they all mean a ratio of one variable over another. And here, our ratio, that slope is always interpreted as a ratio, as an average ratio of the response variable, the y, over the explanatory variable, the x. So here we can interpret that on average, in a linear sense, we may have started with 500, but in a linear sense, we're increasing each day by about 1,300 cases. That anytime we have a linear model, the slope can be interpreted as how fast the y is changing, the response variation changing with respect to a change of 1 in the explanatory or x direction. So for each day we're increasing, that red line was increasing. Let me bring back that red line, because I've just been sitting here talking. As you go along that red line, you're increasing by 1,300 active cases a day. And notice at first the increase around in here, the first few days, the increase wasn't that much. And in here, the increase is more than that much. But on average, the increase is about 1,300 active cases a day. And that's how to interpret that. Okay? Let's go back to that. All right. Okay. Now, so what? I often ask myself that in mathematics, and I don't think that's a mathematics question. I think that's a general question. So what? Okay, you've got this figured out. What can we do with it? Well, a model can be used, any kind of model, like a regression model, can be used to make predictions. And remember what I said. There's interpolation when you're making predictions about when you use explanatory data values, x values, that are within your data range, and extrapolations when you're using x values that are outside of your data range. So here, let's see, this was up to day 11. Let's see what our model says should be the number of active cases at the end of 2 weeks on day 14. Now the way to do that, let's go up here, you go under options and edit. And if you look through all of these, and I know this is complicated. I think Dr. Taylor and I both agree that this is complicated, but it's not unneededly complicated. Everything looks like this. Everything is complicated like this. You want to do real world work? This is the way it is. But don't make the mistake of thinking because I can go right to the spot that I need, that's how I started. You have to look, and you look through, and then suddenly, if you look through this, you'll see prediction of y. And here, and I've already wrote it in, as you can see, I was preparing. I'm going to write in 14. Okay? Let's not worry about what the level means. I'm just going to write in 14, and then I'm going to say compute. 14 as in the 14th day, which is 2 weeks. Now it jumps over here. I'm going to move it back. Let's look at this. So if you will look right here under predicted values, we've got 14. And it's predicting that we have 16,000 300 active cases. And that's if each day we're increasing by our slope on the fitted line. Okay? Now that's an extrapolation because we're asking it a few days further. Now, what the text and I and Dr. Taylor would say to you is that a model is extremely useful in telling us what's going to happen in the future. But the further out you go, the less you can depend upon your model, the less you can believe on your model. The larger the interval of possibilities that you have to think beyond the value of your model. Okay? If you'll look here, the confidence interval for this is between a little over 13,000 and a little over 19,000. So there's some statistics going on there saying that, hey, actually just using some basic statistics, we think that you can say, okay, I'm 95% confident that in 14 days I'll be between 13,000 and some and 19,000 and some. Again, though, that's assuming that the linear model is even close in 14 days. Let's go back to our data. So I'm going to go back to our data and look at what the truth is at 14,000. There's the truth. Look at that. The truth is that China had almost 26,000 active cases in 1 week, in 14 days. Why is that? Because the linear model fails in the long term. In calculus, one of the major ideas that you learn is that when you zoom in into any kind of situation, if you get close enough, the linear model, a straight line, works. If you get close enough to any data, a straight line works. But as you back out and look over a longer range, you have to understand that that no longer holds true. That much more complicated models need to be employed. And you've seen the pictures of the models where it starts curving up and grows exponentially until it curves off and stops growing at all and then bounces down. And that's what's going on here. We are hitting an exponential increase, which is way bigger than the linear model. Okay? But I'm interested in going back and looking at the US data. So here's what I want to do. I'm going to collect the active cases for the US model. And let's look at this. So I'm going to copy, and I am going to go back to StatCrunch, move this over, and I'm going to paste this value in, and paste it in. Control V, boom. So the US, I'm starting day 0 with 508 cases, where in China it started at 502 cases. That's pretty close, okay? And I'm interested in, and let's name this variable. I haven't even, it must have been at some point, let's see, active China. And let's call this one active USA. Okay? Now, what I'd like to do is I'm going to close that one. I'm going to go up under stats and go under regression, simple linear. And what am I going to use for my x variable? Number of days. But what am I going to use for my y variable? Active USA, not active China. Okay? For the first 11 days. And I am going to compute. Now here is my linear model right here. Notice that my r squared's a little less at 78%, but still, that's awfully close to 80% that we saw 90%, sorry, that we saw a second ago. So there's more variation in the US model, at least over the first 11 days, as far as nonlinear variation. Okay, let's look at what the graph looks like. So there we go. Okay? Now, one of the things that kills the prediction is that on day 11 it jumps. The US jumps. So it doesn't jump exponential. So I think if it was the Chinese data, it would have landed right here. But it does a serious jump that seems to be almost hyper exponential. That happened also with the Chinese data later when they redefined and got a better testing to figure out that there was a whole group of people that were active cases that they didn't think was active cases. So it was a big jump here. That's not what happened here. I imagine that there was new testing that went online here and not a redefinition. Okay? So anyway, we're still at pushing 80% of the variation being explainable in a linear sense. But let's go back and look at our linear equation. So again, we've got the negative y-intercept, which means if this really were linear, it would backtrack on the 0th day. There would be negative number of cases, which is just an indicator that this is non-linear ultimately. But I want you to look at this slope here, which is 924 cases per day. Now remember, the other slope for the Chinese for this first 11 days was 1,300 active cases per day. So in a linear sense, if we just looked at, if this were linear on the first almost 2 weeks, in a week and a half, the cases were increasing at about 1,300 cases a day in mainland China. But in the U.S., when it finally got to 500 cases in the U.S., at that point, we were only increasing at 900 cases per day. So what we did is that the rate of expansion of the infection was much lower at the 500 case. Now, some people would say, well, duh, we knew it was coming, and it was very important that we get that rate of infection as low as possible so that we do not overwhelm our health system. That yes, lots of people were going to get infected, but the rate at which they get infected, we need to keep down so that the number of people who needed ventilators and oxygen and hospital care would be as low as possible, not to overwhelm our health system. But we also saw it coming for a month, or at least 2 weeks. We had a 2-week head start. So one would say, duh, we should have known and have taken the most basic of precautions, would have kept that at a lower rate. So that's good. We have started this whole game at a lower rate. Now, so in my last step, I'd like to go ahead and look at all of the data. So I'm going to go back to the China data and let's collect all this data all the way down. I think it's 50 some days. Yeah, 57 days. Let's see, let's copy that. Let's go back to Stats Crunch. I'll come right here and copy it in. Good. And I'm just going to do a linear regression on this. And that will also give me, it'll do a linear regression, but it'll also give me a nice scatter plot of all the data. So number of days and active China, and then we'll do compute. Now, here notice my R squared is barely 1%, which tells me this is very nonlinear, and once you see the data, you will know it, and you should not be surprised. You should be able to probably, as college educated, guess what the data looks like. So there it is. And there's this line there that so what? It's almost horizontal because it goes up, and notice that first line that we plotted was around this area, but then it goes up, and then it curves down. And that's the model that we're expecting. This big jump right here was caused artificially by some redefinitions and some retesting. But we get a very classic infection curve here. And now they're down around the 7,000 mark. because lots of people have become infected. So the number of people that can actually be infected and infect new people, and the pool of new people that are available to be infected is much smaller. So this is what happens, and this is what we are looking for in the U.S. infection rate. Except remember that we started this curve off, instead of the 1,300 infection rate, linearly infection rate per day, we started at 900 infection rate over the first 11 days. So what we're hoping is that this curve is lower, but it just means that it will be longer, because there's a big difference between slowing the rate of infection, new infections, and limiting the number of people who actually get infected. That usually requires something like a vaccine to do. And here we don't have a vaccine, so what we're just trying to do is take this number of people, well, something akin to that in the U.S., and spread it out over more days. But this is over 50-some days, so to get this peak here down, 50 days, we might need like 70, 80, 90 days to spread that out. And that's 3 months. Okay, so let's do a review. Okay, so let's go to our Moodle course, and let's open up that data, this height versus wingspan data, and let's walk through all the things that we talked about. Okay, we're trying to interpret the different pieces of the linear model, what an R squared means, and interpolation and extrapolation. Okay, so let's open up the heights and wingspan data. All right, so there's our heights, there's our wingspan. Come on. There we go. So we'll copy that, and then we'll come back to our stats crunch. And I think we can just, let's see, we'll delete that. And session applets. Can't we go new data table? Maybe we can do that. Okay, here we go. New data table. Blah, blah, blah. Run, run, run. Yay, yay, yay. And we will paste that in. And going back and trying to remind myself, height and wingspan. Okay, so I'll change this variable to height and wingspan. And you should be able to do this too. This is all the data that you have available that we're pulling right off. All right, so this is the inches in height. This is the inches in, boop, from arm to arm. Okay, I'm just making sure you can see it. Okay, so let's go to regression, simple linear regression, and compute. What? Oh, duh, I have to choose my x variable. So let's let this misspelled height word, oh my god, to be our explanatory variable. And let's let wingspan be our response variable. Could I have switched the two? Absolutely. Because this is a classic example of why I don't think height forces wingspan, causes wingspan, arm span. And I don't see why wingspan would force height. They're just correlated, not causing each other. All right, so let's compute that. And what do we get? Well, we get a model here that says, okay, at a 0 height, what should your wingspan be? Well, you would think, okay, my wingspan should be 0. And sometimes we can actually in this case we could too, we can force linear regression to have a y-intercept of something that makes sense at 0. But here it's just saying, if you start using this regression as something ridiculous like 0 height, I'm going to be ridiculous too at negative 6.8 inches, negative inches, so you're in another dimension. But what it's saying is that my arm span is increasing by a little more than 1 times my height. So each inch of my height increases my arm span by a little more than 1. Okay, just a hair or more. So kind of like it's 1.109, so 1.1, so by 10%. So if each step for each end of my height, my wingspan goes 1.1 inches. Okay, now let's go on and see a graph of this. And there is my linear regression. And you might say, okay, this goes out to 75 feet. What about mine? What is the predicted wingspan of me? Well, I'm 6 foot 5 inches. Let's say 6 times 12 is 60. 72 plus 5, that's 77. That's an extrapolation. But it's awfully close to this. It doesn't look like anything is more than 77. But let's go back and see what this says my wingspan should be if I'm 77 inches tall. Let's make sure I'm right about that. 6 foot 5. 6 times 12 is 60. 72 plus 5, 77. Okay, so let's do this. We go into edit on the option. And we come down here and we put in 77. And let's compute and see what do we get. Okay, just moving this over. What do we get? It says that my wingspan should be almost 78 inches. So it really doesn't, this really just kind of confirms that your reach on your arms, this is what I'm doing with my arms, is about your height. Okay? But it would be much better to notice that if I say I'm only 5 inches tall, it would give a ridiculous number. Suppose I'm a 5-inch tall person. So let's go in and go, I am 5 inches. Where do I go? Right here, 5 inches. 5, compute. So what do I get? I get that my arm span is a little under -1 inch. That makes no sense. That's like this. It makes no sense. And so there's a big lesson. Extrapolation is useful, but unless you understand much more about the model, unless your model is fixing much that takes into account lots of things, regressing the data down to a linear model will give you a rough model for what's going on in your data range, but it's really probably not a good model if you go too far outside of that. Now, when you're within your data range, what is that called? Interpolation. When you're outside your data range, what is that called? Extrapolation. Hey, I had a good time talking to you about this. We're going to get through this whole virus thing. We're going to learn lots of statistics, and I can't wait to see you again. Okay? Bye-bye.